In a remote corner of Norway, far above the Arctic Circle, lies the Svalbard Seed Vault, a symbol of humanity's dedication to preserving biodiversity. Housing the seeds of virtually every plant species on Earth, it serves as a safeguard against extinction. Yet as our planet faces the pressing threat of rising sea levels, even this fortress of biodiversity is not immune to risk. Scientists propose an audacious solution, storing these precious seeds cryogenically within the moon's lava tubes. But with this ambitious plan comes a monumental challenge. How do we transport these vital resources back to Earth? Our mission begins on Earth, where the CubeSat is loaded into the Falcon 9 rocket module alongside other CubeSat missions. Once the rocket is in orbit, it will deploy our project into LEO. The solar panels are then deployed from all sides to begin power collection to ensure the mission sustains its required runtime. Next, the Terrarium is extended from the structure using our scissor lift system in order to reduce the necessary amount of rotational speed to simulate artificial gravity, which puts less stress on our structure and preserves our power supply. Finally, the rotation begins, which signals the start of our scientific mission to analyze the effects of our system on the fungus.
What was the biggest challenge in ensuring the structural integrity of the CubeSat while incorporating the scissor lift system and Terrarium?
The biggest challenge was ultimately just the space we had to work with. Our goal was to maximize the amount of space we have available for our experimental terrarium chamber. And originally we opted for a custom truss structure, which while strong enough, it was about 5 millimeters thick. And this left us with only about a 90 millimeter square footprint for our terrarium to exist in. And so this is one of the reasons that we switched to an ISISpace 3U CubeSat, one more proven than what we would have been working with otherwise.
The frame has extensive testing and history, with flight heritage dating back to 2013. Coming in at much thinner at about 2 millimeters, we've got it cut out of aluminum 6061 T6 and are welding it together. We've also implemented a scissor lift mechanism to extend the terrarium as far as possible. Since we are inducing artificial gravity on the terrarium, the CubeSat must be in a constant state of spinning. Because the force on the terrarium has acting on it is a function of the radius as well as the rotational velocity, we have two options for how we can get the artificial gravity that we want. Increasing the speed means a higher power requirement for the reaction wheels in the GNC compartment. The other option would be to extend the terrarium as far away as possible from the center of mass. We used a combination of both of these methods. Our scissor lift is driven by a micro metal gear motor coupled with a 540 lead screw. This drives the scissor lift arms forwards and backwards.
Could you explain the organization of the CubeSat and the challenge with maintaining functionality and efficiency?
Yeah, so the CubeSat stack serves as sort of our central core of our satellite, and it contains all of the vital components such as the communication system, the onboard computer, and the power supply. And definitely the most difficult part of organizing everything was maintaining the functionality and the practicality of each system, and making sure that there was really no interference across any of the systems, whether that be with respect to our wiring or any of the spacing of any of the specific components.
As we descend the layers of our CubeSat stack, we first encounter the antenna array system, a critical component facilitating the communication with Earth and the ground team of the mission. Moving down, we arrive at the Attitude Determination and Control System, or ADCS module, responsible for orienting the satellite in space. Continuing, we reach the BeagleBone Black configuration of the onboard computer, the brain of our satellite, orchestrating its operations in conjunction with all other aspects of the satellite. Further along, we encounter the battery system, providing power to all subsystems and ensuring continuous functionality for all other systems in the CubeSat. Finally, we find the payload driver board, governing the payload's operations and data acquisition. Together, these layers form the backbone of our CubeSat, enabling the mission to unfold seamlessly.
What was the biggest consideration that you took into account when you were developing the power system?
The mass and volume constraints of a 3U CubeSat limit the size of the power supply. Also, it's uncommon to conduct science within a CubeSat. Therefore, the size and power requirements of the instruments we selected needed to be carefully considered to prove that this concept is feasible. Once components were selected, we began designing the power system by analyzing the voltage requirements for each component. Power needs to be supplied directly to the Raspberry Pi, the motor, the IR lights, and the water pump. Since the pump and lights need 12 volts, we decided to use a 12-volt lithium-ion polymer battery to eliminate the need for an external power supply and to accurately reflect our conceptual design with a rechargeable power source. We also had to consider the amp-hour output of the battery to make sure that our system could maintain power on design day. After that, we added an additional step-down component to supply 5 volts to the Pi. The Pi then supplies 3.3 volts to the sensors and camera. We decided to use a MOSFET switch to control the IR lights and DC motor controllers to control the water pump and motor.
Could you explain the difficulties of fostering a fungus in a completely closed environment?
So the difficulties of growing a fungus in a completely closed environment is that you have to replicate the environment outdoors, indoors, without any human interactions. That means water has to be stored within the chamber, heating and cooling has to be applied in the chamber so growth can be promoted. All this while not being interacted with by human hands. The automation begins with a water reclamation system, which will take water from a tank and pump it into the terrarium. Whatever drips through can then be recycled. There will be IR lights stuck to the surroundings of the terrarium, which will function on a temperature feedback loop to radiate the plant to the correct temperature. Even with these stopgaps, there are still issues inherent to the process. No cooling, a lack of soil depth, a compressed space. These are risks which have been taken for the process, necessary for the specimen to grow in these unique conditions.
What was the process like for selecting the instruments to be used in the terrarium?
The process for selecting instruments was derived from critical life support variables. Critical life support variables were determined to be temperature, humidity, pressure, and CO2 content. Temperature and humidity need to be controlled to mimic the proper habitat of the mushroom. Pressure is measured to demonstrate proper enclosure of the terrarium. Mushroom growth is dependent on CO2 content, therefore having this measurement is pivotal to understanding the compatibility of the enclosure of the mushroom.
In order to monitor and control these critical life support variables, a Raspberry Pi 3A Plus is used as the sole onboard computer. Using the I2C pins located on the computer, a BME680 and SGP30 are used to measure all needed habitat parameters. Using MQTT, a versatile machine-to-machine messaging protocol, the data is transmitted to Node-RED as a JSON. Node-RED characterizes the data as the proper critical variable and passes the information to its respective location in a database. The database, InfluxDB, is then queried by the graphical interface Grafana, which then provides an elegant solution for data visualization. The Raspberry Pi not only executes the data handling, but as well as the control of the temperature, humidity, and scissor lift. Configuring one of the GPIO pins to output a PWM signal, the Raspberry Pi controls the scissor lift and water pump. The IR lights are configured with a MOSFET controller that takes a simple high, 1, or low, 0 signal from the GPIO pin to turn on or off the heat source. Using the sensors as feedback, the terrarium is able to maintain proper habitat conditions.
Looking forward, our project marks just the beginning. Beyond this endeavor, there's a plethora of unexplored ideas to delve into when it comes to Centrifuge CubeSat terrariums. We need to further investigate the long-term sustainability of the closed ecological systems in space, and we also have to tackle issues like waste management and ecosystem stability within the terrarium itself. So as we wrap up here, we're already envisioning what the next senior design projects could look like, which could confront the topics of how these seeds will be stored on the moon and what one of these facilities might look like.